We're back with NASA Administrator Charlie Bolden and NASA Edge co-host. Now, Charlie, we have an important launch today, this morning, with the SMAP satellite, and it's all part of the looking at the global climate change. I mean, how important is this SMAP mission?
This mission is very critical. It's the fifth and final of my what we call the Year of Earth. So in 11 months, we will have launched 5 Earth science missions, which is sort of unprecedented. And this one, for a couple of reasons, really finishes out the suite, because this allows us to look at global moisture in the soils. It also allows us to differentiate from space between frozen tundra and just regular old turf, which my scientists tell me, I'm not going to pretend to understand it all, but they tell me that's very, very important to understanding the CO2 cycle. And we believe that's one of the big contributors to climate change, so the more we understand about it, the better. The other thing that SMAP allows us to do, and I do like this stuff, because as a pilot flying radar every once in a while, you always want to be able to see small chunks.
Right.
And so up until now, up until SMAP, we saw big chunks of Earth, like 25-mile resolution.
Right.
SMAP is going to drop that to a quarter, so we're going to actually be able to see pieces of Earth in terms of a 6-mile sector. It also is going to look more frequently. So you want to be able to look as often as you can if you're trying to understand climate, make weather forecasts and like. And you want to be able to see as small a chunk of Earth as you can. And so SMAP gives us both of those in this one mission. So it's critical.
From a technology standpoint, it's amazing how we're going to be able to actually look at 5 centimeters in the soil and determine the moisture content. It's great. It's
well,
amazing.
The other thing is the fact that you can now discern between freeze and thaw. So you can look from space and determine whether you're looking at frozen ground that's causing CO2 to go back out into the atmosphere, or whether you're using it because you've got vegetation and everything else that's using it in photosynthesis and other things.
Now, SMAP is not the only satellite that's going up on the Delta II. We have some CubeSats on board.
As a matter of fact, and I don't think I'll get in trouble if I do this, but go ahead and ask your question while I try to get my tool.
You're getting your tool out. Oh, there you go.
They didn't ask me to do this, but I will do this. This is for the
Alana 10 mission.
This is for all of you who are the CubeSat guys, who are right next door here, as a matter of fact. I accused them all of being from high school. They were not. They're in college, and some of them are in grad school, and others are adults, but they all look like kids. But they're flying these things that are not much. When you sit it down on the coffee table, it's actually about the size of that. So that's the footprint of a CubeSat, and we're enabling high school students, college students, and everybody to learn how to send things to space. And they're putting them in small packages that are relatively inexpensive and learning lots about Earth.
Now, when we look at SMAP, the soil moisture active passive, what is that? What's the importance of that satellite?
Well, I mean, scientifically, it's important because it closes a gap that we have in our models about climate change. We're not really sure whether, as climate changes, we'll see more or less soil moisture. And you can imagine water in the soil is critical for plant growth, for human life, for the growth of produce and livestock. So launching the SMAP mission gives us this ability to make these global measurements, the first ever global measurements that enhance our ability to predict both weather and climate. It's critical to all of us.
Now, when you look at the name soil moisture active passive, what does that mean by active passive?
Well, there's an instrument, a single instrument reflector, that large antenna that you see. And we have a radar and radiometer that use that reflector to combine the RF energy and get it into the spacecraft back from the ground. Half of the instrument is a passive measurement. It measures energy from the ground. We call it brightness temperature. And the brightness temperature is a measure of how much moisture is in the soil. The active part is, in effect, us sending radio waves to the reflector and then bouncing them off of the Earth and back again. So some is just listening, some is sending and listening. That's why it's called active and passive.
Now, from my understanding, is you're actually going to be looking at the soil moisture content in the top 5 centimeter layer of the Earth?
Well, that's correct. The particular orbit that we have allows us to measure the soil moisture across the planet every 3 days. So every 3 days we get a picture of the totality of soil moisture for the entire planet. And every 8 days it repeats exactly. So this would be the first time we get global measurements of soil moisture or the water content of our soil across the world ever, in human existence. The resolution that's provided by the radiometer, the 10-kilometer resolution for soil moisture and the 3-kilometer soil moisture resolution, allows us to look at the freeze-thaw state, so we can see when the vegetation growing season might change and therefore how much carbon gets taken up by the atmosphere.
Right.
And that's a critical element in understanding how much carbon we pull out of the atmosphere when we start to think about greenhouse gases and things like that.
This provides a gap, I guess you could say, in the models in
Well,
terms
yes.
of predicting climate change?
Again, we're not sure as a function of climate change whether or not we wind up with more moisture in the soil or less, whether or not we see more droughts or floods and where those might occur. Soil moisture is a critical element in understanding how those weather pattern changes and how much soil moisture there is. Imagine it's very similar to perspiration. The water at the surface of the earth is a cooling agent in some ways and evaporates into the atmosphere for rain and allows the planet's temperature to change.
Right.
So when you understand that missing component, you start to understand better how the weather and climate is going to change for the planet.
Now, looking from an engineering side, what were some of the challenges of designing that satellite? Because it looks like it rotates, the top half rotates one way and the bottom half rotates the other way. But can you kind of explain that?
Well, originally we were on a much smaller rocket launch vehicle, is
Okay.
what we call it, and packaging that large reflector that you see, it's a 6-meter reflector, it's about 20 feet in diameter, squeezing that whole thing down, much like origami, into a package that could fit into the rocket and then open up to that large size that you see on orbit was a challenge. But in addition to that, that large rotating reflector is inertially significant, right? It wants to spin that little spacecraft that's about the size of a refrigerator below it. And that was a technical challenge. How do you spin this large thing with this little thing and keep the whole thing from wobbling?
Right. How difficult is it? Because you're getting that data, the data's coming back up, it's hitting the sensor, and then it's getting funneled
That's
down
right,
through the
into
funnel?
That's correct. Imagine it's very similar to, I don't know how best to describe it, standing in the middle of one of those kid playground things where you spin and you're holding a magnifying glass and trying to look at an ant on the ground, right? You're sort of shaking around and at the same time trying to look at the ant. So the SMAP spacecraft has to maintain its attitude while spinning this very
Right.
large reflector above it to make these soil moisture measurements.
Now, project system engineer, not systems, but system engineer.
Yes.
Explain your role in the mission.
Well, I'm sort of the technical integration function for the mission. We have a mission system that defines how we communicate with the spacecraft, how we command it, how we get signals down by the antennas, those large antennas you see. We have an instrument system that's developed the reflector, the radar and radiometer that make the active and passive measurements. We have the spacecraft, which is effectively the vehicle that carries that instrument around. My responsibility is to make sure that the interfaces and requirements across all of those elements play out correctly so the systems work together, and then ultimately we test it and we've got the right design, vision, and architecture to do the mission that we need to do for the science.
So you're sort of the go-between between the scientists and the engineers.
Sort of,
So
I
the
guess
broker,
I am.
yeah.
I'm sort of the broker,
Yeah.
right? I'm a negotiating agent across those
You got to
elements.
make everybody happy in your job, don't you?
I don't have to make them all happy, but they all have to work together.
Right. And make sure that you have mission success.
Exactly.
Well, Shawn, I want to thank you so much for coming out here on the second attempt.
Thank you
and
very much. It's a pleasure being here. I'm
and-
glad you had me back again.
And hopefully we'll get the Delta II up and SMAP ready to go.
I believe we will. I believe we will.
And what we're going to do now is I had a chance to talk with Lieutenant Colonel Brande Walton of the United States Air Force earlier this week, and we're going to look at what the Air Force's role is in the launch of the Delta II. Colonel Walton, what's your role at the 30th Space Wing at Vandenberg Air Force Base?
So as the commander of the 2nd Range Operations Squadron, primary mission is command and control of the Western Range. So that includes mission assurance, but mostly public safety. So we want to make sure that air, land, and sea is safe for launch and after launch.
Now, when you talk about public safety, what are some examples of public safety for a typical launch here at Vandenberg?
So there's many facets of public safety, and we have to, again, make sure that all facets are good and go for launch. So for land, we have to make sure that within the area in which it's launching, that there are not people in that area. So for example, we make sure that we have Amtrak trains that go through. We will actually hold the train prior to launch to make sure that, again, we're keeping the public safe. For air, we make sure that no aircraft are flying through the corridors. For sea, we make sure that there are no boats in the specific protected areas, so we don't want anybody just watching the launch and, you could have a danger there. And then we make sure our instrumentation is go. So for that, can it track the vehicle? Because we have to make sure that we can track the vehicle. We always know where the vehicle is at minus count in case it's performing erratically.
So if you had a situation where you had a boat, or if you had maybe a surfer out in the water, or someone who's just driving through and not really know what's going on, I mean, that could be grounds for delaying the launch or
It could. There's a lot of rules with it. One surfer probably not going to delay the
Right.
launch, but if there's a boat going through, then we will take information, and then our LDA, again, our Launch Decisional Authority, with safety, will then make the ruling on if they're a go or no go. So there's a lot of rules that go with it.
In this particular case, when NASA comes to Vandenberg Air Force Base to launch a satellite along with the CubeSats into space, it's, I guess, more of a logistics challenge because now you have a partnership between NASA, the Air Force, and in this case ULA, which is in charge of the launch vehicle. How is it challenging for all those entities to work together as a team?
It's not challenging. We do that for every mission, but we do have to make sure that we're lockstep with each partner. So with NASA, with ULA, and then again with the Air Force team. For example, today we had a crew academic session with the range, and we invited both NASA and ULA in to make sure that we were all on the same page and how we're going to do our crew procedures and march through the minus count of the launch.
Now, as commander, where are you going to be watching the launch from?
So as the commander of 2 ROPS, I am always in the, what we call it the ROC, Western Range Control Center, and I serve a role kind of as intermediary. So I want to make sure that all portions of the launch are going smoothly, and then if there's any hiccups, that I can be there to help control that.
And one final question, does it ever get old to see these rockets take off from Vandenberg?
It never gets old. Yeah, never for me. I used to work on the Eastern Range as well, so I've seen all kinds of launches. I saw the space shuttle. I worked as a mission flight control officer. Every one, I always hold my breath. And it's always great in the ROC because you can feel it and you can hear the rumble.
It seems like the rockets are much closer here than they are down in Florida and Kennedy. It's maybe because of the mountains or the hills, I don't know.
You can definitely feel it and hear it, yeah, depending where you are. You can usually see it. If it's not foggy, we get a lot of fog, but it never gets old.
3, 2, engine start. 0, and liftoff of the Delta II rocket with OCO2.
I'm here with Joe Sims, who is an advanced orbital analyst with JSPOC. Joe, exactly what is JSPOC?
So the JSPOC is the Joint Space Operations Center. It is U.S. Stratcom's operations center that's in charge of space and things that go through space, or is, I guess, resident in space. Currently, there are just a little under 20,000 objects that the JSPOC tracks. Those are on-orbit objects to include active satellites, pieces of debris, the rocket bodies that place the satellites in orbit, as well as anything that travels through space, test vehicles, things of that nature.
We're going to be launching some CubeSats today. Exactly how do you track something that small once it's released from the vehicle?
So the JSPOC uses a network of sensors, a mix of optical sensors and radar sensors, to track those objects. So while a CubeSat, a 3U CubeSat, which is rather small, we're still able to track them. They present a smaller profile than some of the larger, more familiar satellites like a GPS satellite or a communication satellite, but they are trackable.
You actually track the debris in space so that when satellites like SMAP are launched, they are delivered safely to orbit, and when the CubeSat's secondary payload is released, they're not going to collide with anything.
Correct. So the JSPOC receives trajectory information from the safety office here at Vandenberg. We take that information and we put it into our software suite. It compares those trajectories against the predictions of all the other objects on orbit, and that helps us ensure that when we do launch SMAP, that it arrives safely to its intended orbit.
You just like plug it in, and it's like return, and it comes back. This is good?
Correct. You know, the farther out you're trying to predict, the more computing horsepower it's going to take to do it. But we typically will do a screening about 7 days prior to the launch to get the first look at what that launch window might actually look like.
Now, when you're looking at your screen and you're looking at the debris and the satellites in space, does it look similar to that of like the airplanes across the United States where you just see all these dots?
It is similar in some screens, yes. Some screens will present a host of dots. Each dot will represent an observation that one of the sensors in the network has taken. It'll string those together into a visual profile of where that object has been, and the software suite will then propagate where we expect the object to be in the future.
Now, there are different orbits around the Earth. Do you know where like the CubeSats are, where the satellites like your DirecTV and Dish networks are located, Are they in different orbits, or are they just all clumped together?
So they're in a host of different orbits. The orbit is generally determined by what the nature of the spacecraft is. So your direct TV satellites, for example, that are beaming down your television, those will be in a geostationary orbit. They maintain a fixed position over the United States, for example, so that you can get reliable and continuous coverage. Other satellites, communication satellites, will be in geostationary orbit as well. Satellites that might take pictures of the Earth for your Google Maps, for example, those will be in a lower orbit, a low Earth orbit, so they can get a good quality picture.
In what orbit will the CubeSats be located?
The main payload for this mission, SMAP, is going to be in a low Earth sun-synchronous orbit, and the CubeSats will be placed in a very similar orbit after the deployment of the primary vehicle.
So when these CubeSats have finished their missions and they just fall back to Earth or burn up in the atmosphere, do you all just like cross them off the log that they are no longer in orbit?
So in a way, we do just cross them off the list. As the prediction for where that satellite will be reaches certain parameters, we'll receive indications that it might be re-entering soon. Once that happens, we'll continue to refine those predictions so that we can try to get the most accurate date and time that we can for when that object should re-enter. And then once we can confirm that it has re-entered, we will add a decay date in the catalog, and that kind of is the period at the end of the sentence for that satellite.
Now, the information that you get as far as the location of this CubeSats when they're in orbit, is that the same type of information you share with the universities and the different organizations that put CubeSats in orbit?
It is, yes. The JSPOC has a Space Situational Awareness Sharing Program, SSA sharing, and a lot of information, mainly two-line element sets, are put out for the public, for research organizations, other governments, other companies, to share that information to make space a safer place for all those that have objects in it.
And now we're joined by Tiffany Nail from the Launch Services Program, who's going to talk about space operations. Now, Tiffany, on Thursday, our launch was scrubbed due to high winds.
Correct.
And usually, if it was just a wind issue, we would come back and try and attempt on Friday morning.
Right.
But there was something else. What happened?
Well, after we took all the liquid out of the rocket and ULA team went up to the launch vehicle and assessed, they found a couple issues with debonding. And debonding is not a big significant thing as long as it's very minimal. And what happened is they assessed it, they fixed it, they put a silicone-based agent on it, but that did delay us another 24 hours because they needed time to fix the problem. So then we look at, for tonight, this is our second launch attempt, and we're back where we were for our first attempt.
So that's the issue right now.
Correct.
We're looking at around 45,000 feet. The winds are too high right now for launch.
Right. What I'm finding out, because this is, I'm getting updates as they come, is we're looking at 74 knots in the 40,000 area, and with upper level winds and a Delta 2, a Delta 2 takes off the pad pretty quick, and you can't really slow that down. So what they're trying to assess, the launch team is trying to assess, is can we steer the rocket into the winds? Can we change its flight profile to go towards the winds? And right now the winds are just so much that it's just not safe for the Delta 2.
Now, how does Launch Services select a rocket based on the payload? In this case, it'll be the SMAP satellite.
Right. We look at two big things, I like to say. The orbit, where does it want to go? And then also, what's the size of the spacecraft? And for SMAP, the perfect size and the right rocket to get to its orbit is a Delta 2.
Talk to me a little bit about the process of the SMAP satellite arriving to Vandenberg and how it's getting prepped for launch.
So the spacecraft arrives around 2 to 3 months before launch. That's different for the rocket. So the Delta 2, you're looking about 3 months probably, because they have to go through processing the launch vehicle at the pad. SMAP, you have to go through testing, spin balance, getting it ready, putting it through its paces of what it's going to go through on the launch vehicle to launch, to get to its destination. So you've got both of them processing in parallel. And then the Delta 2, this is United Launch Alliance's rocket. So the Atlas V, if you want to do a comparison, the Atlas V only needs 3.5 weeks to process, because the difference is it doesn't have to go to the pad and get testing as much as the Delta II. And that's the reason also is the Atlas V is a newer rocket and they use newer hardware. So that gives your audience a kind of difference between the two ULA rockets.
Now, after this mission, Launch Services program has, other launches on the docket. What's coming up for it?
That is correct. Our next launch is the MMS. It's going to be launching from Florida, and it's looking at March 12th in an evening launch.
Now, MMS, as if you've been watching NASA Edge, that's the magnetospheric multi-scale mission. We will be live in Florida for that launch coming up in March. So we want to make sure everybody stay tuned for that. Tiffany, thanks for being on the show today, and hopefully those winds will die down and we will get a successful launch.
T-minus 15 seconds.
Go Delta. Go SMAP.
Green board. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engines start and liftoff of the Delta II rocket with SMAP, making global observations of soil moisture for climate forecasting.
Man, great launch.
Well, it's kind of funny because we all went outside to go see the launch behind Building 836 here at Vandenberg Air Force Base. We saw it light up, and we saw it for about 3 seconds, and then that was it. It was in the clouds, and it was gone.
Because it's cloudy around here today, I just saw the area around the launch pad just got bright, and the fog lit up. And after that,
it was it.
That was it. I didn't see anything.
But it really lit up the sky for that brief period of time.
Yeah. But SMAP is underway. And it is now a countdown to actually deployment of SMAP and then the deployment of the CubeSats.
Right.
And that will lead us into the second part of our program.
And we're going to do that about an hour from now. We're going to come back for the deployment of the CubeSats, and we're going to have a whole show, a slew of guests. We'll have students who are part of the CubeSats that are on board the Delta II. And we're still going to see if we can actually find Blair. We tried calling him, but no answer. Getting a little concerned because his GPS, he's not very good at the GPS.
Yeah, even with the technology, but hopefully he will make it on board and he will be here for the second half of the show.
You're watching NASA Edge.
An inside and outside look at all things NASA.